Okay, let's look at written homework 12.1. We're going to do a chi-square test. Here we're looking to see if we observe something, if what we observe is what we expect to observe based off a distribution of, of a given distribution. And again, this first problem is like the example we did in notes with M&Ms, and so we assume this type of distribution. You get a bag of M&Ms, a total of 400, and these are the colors you got. Does this match up to what we would expect to see if this is the correct distribution? So in order to run a chi-squared goodness of fit test, you have to determine what the expected values are. So here's the observed values, is what we got in the bag. And then expected values come from the percent times the 400, right? This is, if it really is 12%, we expect 48 brown. If yellow is 15%, we expect 60. 15% of 400 is 60, and so forth. And so that's where the expected comes from. And to run a chi-squared, again, the calculators are pretty simple. They're just tedious. You take the observed minus the expected, square that, divide it by the expected, add all that up, and that gives you your chi-square test statistic. And then once you have the test statistic with appropriate degrees of freedom, you can calculate the chi-squared using the chi-square calculator, and you get your p-value there. And so with so once you have that, you can then compare to decide to not reject or reject, right, which is our null hypothesis and alternative. And the p-value is so big that we do not reject. If you're going to use StatCrunch, which I suggest, you have the observed colors and expected colors. It's, again, goodness of fit, chi-square test, observed, expected, and then that's it. You compute it. And then notice then you get that p-value and a chi-square, which matches up what we have here and here. So you do not reject this. So what we're saying is there's not sufficient evidence to conclude that there's a difference. So we're saying that we think that the distribution matches up based off of the expected and observed values. And so that's for number 12. Number 16 is a little bit more difficult, a little bit more calculations to do before we get to the test. But here's the members of Congress and the religion they are, their religious affiliation, and then a random sample of 1,200 adult Americans and their religious affiliation. So what we're trying to see is the distribution of the religions in Congress. Does that match up to the distribution we would expect to see in the public if they matched up with Congress, or if they had the same distribution? So first thing is we need to make a probability distribution. So 52% are Protestant, 30% are Catholic, and again, it's based off of this total here, 535 Congress members. 306 divided by 535 gives you these numbers. And then with those numbers, we can then determine, here's what we observed, and then if the public followed this distribution right here, then we would get these expected values here. And once you have the observed, which we got here, and then the expected, we can either, again, write your null and alternative, given that the distribution is the same as Congress, our public one, or that it isn't the same. And you can do all those values, get your p-value. In this case, the p-value is really small. The chi-square is really big, so we reject the null hypothesis. We do say there is sufficient evidence that the American population religious distribution is different than Congress. And so that becomes our conclusion. Again, if we're going to do that, here's observed and expected right here. You would run that again. Let's turn this to observed and expected. Compute, and you see you get, again, a p-value. It's really small, big chi-square. And so from there we have, again, from this situation, we reject the null hypothesis there. And then the last one here is, here are the number of deaths during the week of bicycle deaths, and we want to know if those are equally distributed, right, across the days. Do certain days have more frequency than the other? So if it was all random, like we had out of 200 deaths, right, if it was all random, we would expect 28.57 per day. That's what we would expect. And so we could run the goodness of fit test again. again, where we would use this is again the hand calculations, observed minus expected, squared divided by expected, and so forth. And again, if we were going to use StatCrunch for that, I have it here already entered in there. Observed fatalities compared to your expected fatalities, you can compute. And so then again, you get a p-value, very small, big, chi-squared. So because of that p-value, you're going to reject the null hypothesis. Reject that, right? So this is not good. So we're going to say there's sufficient evidence that the bike fatalities do not have equal frequency on each day. So there's a difference in the deaths on different days. They're not all the same. At least statistically, they're not. And so that's what we have there.